Today is this is literally the last day of lecture. I mean, I haven't decided what to do yet. Maybe we'll just do in-class work on problems. We have a lot of class left, but I could also just go into some topics as kind of like seminar style where I just don't give you assignments. I'm sort of thinking about it.
You could go over like really rare instances of how to use stuff.
Yeah. I'd have to think of what those are, though.
Like forest items,
Oh.
stuff like that.
Oh my gosh. We're not ready for that.
No.
You're right that's a leads to complicated math.
That's
Yeah.
like a sponge or something.
Yeah. It does get complicated. Non-homogeneous bodies. I know. Actually, my master's advisor did his PhD on non-homogeneous material mechanics.
Is fiberglass not homogeneous? Or in like
I don't know.
carbon fiber?
Well, I'm sure, I mean, anything that has a noticeable grain direction is not isotropic.
Yeah.
It might be homogeneous, but it has different behaviors in different directions.
Yeah.
So then you got that problem to worry about. I mean, I would think like carbon fiber would be homogeneous, but just not isotropic. But either of those would, keep us from using the techniques we've been using. Yeah, well, I think mostly OceanGate gave us an example of why you don't want to trust carbon fiber under like extreme cyclical loads. I think that's what happened was the layers, delaminated and it's really hard to detect that.
It's impossible to like make all the layers bond perfectly.
Yeah.
You're eventually gonna get a
Yeah. Okay, let's do this though. Let's do this stuff first.
You know that. They tried to
Yeah.
make airplanes out of it.
Oh, okay.
They gave up. They're like,
Yeah. Okay, so what we're talking about is, we're talking about column buckling. And we are now doing calculations where the column is fixed at the base. And from considering just the stuff at the base, we have the solution deflection as a function of x is equal to m sub 0 over p times the cosine of the square root of p over ei times x minus m sub 0 over p. And now it's just a matter of using boundary conditions away from the base. So we'll use the remaining boundary conditions to find the critical load value. So the first one we did is we assumed free at the top. Bless you. And being free at the top meant that there was no couple at the top, no bending moment at x equals L. And so that said that the deflection double prime was equal to 0. And that gave us the answer, P critical is equal to EI pi squared over 4L squared. So we got that last time. And now we're going to go back to this that you can think of as like the solution that sort of defines fixed at the base. And now our boundary condition is going to be pinned at the top. And we'll see how that changes things. So if it's pinned at x equals L, what does that mean about the deflection at x equals L? Like, what do we know about V if it's pinned at the top?
V equals 0.
V equals 0. And then do we know anything about V prime? No, that's only at, okay, so V at L is equal to 0. We don't know anything about V prime because you can imagine, you know, something pinned at the top could have a shape like this, where at this point here, well, this is fixed at the bottom, so down here it couldn't have that. But you can see how the slope of the deflection at x equals L in this case is not 0. So we can't assume that. Okay, so we have that m sub 0 over p times the cosine of square root of p over ei times L minus m sub 0 over p is equal to 0. And you can divide everything by m sub 0 over p. And what this requires is that the cosine of this is equal to 1. Okay, so where is cosine equal to 1? Our requirement is going to be that square root of p over ei times L is equal to n times 2 pi where n equals 1, 2. Okay. So now we'll square everything and we get, okay, p over ei times L squared is equal to n squared times 4 times pi squared. And so P critical is equal to 4 EI pi squared over L squared.
So we just choose n equals 1.
Yeah, yep. We're always choosing the lowest non-trivial n. So n equals 0. I mean, actually n equals 0 is also a solution to this. I didn't write it in there, but that's a trivial solution.
So are there any situations where n won't equal 1?
Well, you could make that boundary condition in different ways. I mean, I could have said that it was, so I mean, I guess I've probably set it up so that 1 is the one that we choose. But, you know, I could have set this up as equals n pi, and then n has to be equal to 0, 2, 4, 6, you know.
Yeah.
And then we take the 2. You're just always taking the lowest non-trivial n.
Got it.
So yeah, it kind of just depends how you define it.
But that would give you the same formula.
The same exact formula, yeah. Yes?
Is there a reason why we pick the lowest non-trivial at?
Yeah, because, that's sort of a good, that's kind of the philosophy of this whole thing is like, we're trying to find the lowest place where we're worried about this thing buckling. You could use it's not that a bigger n doesn't give a solution, it's that the thing is already buckled by that point. Because notice that as you go to higher n's, you're going to higher forces, And so, in a sense, in the case where we have a restraint at the center, that's what we're kind of doing, is taking a different n value that satisfies that middle condition. Okay. So let's do one more and then we'll list these all out so that you get kind of an intuitive sense of, what has a bigger critical value. So now we're going to do a boundary condition. Where we have a pin at the center. We did this with pinned ends. This is x equals L over 2. And we have our equation that says m sub 0 over p times the cosine of square root of p over ei times L over 2 is equal to m sub 0 over p. And so square root of p over ei times L over 2 is equal to, so we're saying that the cosine is equal to 1 again. So this is equal to n times 2 pi again. Square both sides, you get p over ei times L squared over 4 is equal to n squared times 4 times pi.
Pi squared.
Yes. Thank you. And so P critical, if we take the n equals 1, the lowest non-trivial solution, we get 16 ei pi squared over L squared. Okay, so now let's go through all of our different cases and just compare I'm going to go from lowest critical p-value to highest. So the lowest one that we saw was fixed at the base, but free at the end. And that had a P critical of ei pi squared over 4 L squared. Next, we had 2 of them. So the first one was no, we're not there yet. We don't have 2 of these. The next one that we see is pinned at the base and the end. And that's a critical p-value of EI pi squared over L squared. Then third, this is the one where we have two. So first, we have pinned at the base, pinned at the center. And that's a critical p-value of 4 EI pi squared over L squared. And then the second one with that same p-value is fixed at the base and pinned at the end. And so that's the same thing. And then the one with the highest critical buckling load is fixed at the base pinned at the center. And the critical p-value there is 16 times EI pi squared over L squared. And so you can see there's a factor of 64 difference between so for the exact same beam, you have a factor of 64 difference between the fixed at the base and free at the end, and the one that's fixed at the base and restrained at the center. Mm-hmm. Okay, so it's a huge difference that you get from these different positions. Yeah. Anybody have any questions about those? Okay, so the questions on this ask you to derive these things. Let's spend the rest of the class just like, I'm going to give you some time to think through the steps and try to make sense out of this derivation. I think you'll be happy you did this later on because you're going to see this equation a lot in the future, and you're going to see it in dynamics very soon. Yeah.
So when you say derive, are we starting with the v of x equations?
Yeah, we're going to start with the
derive from the scratch where we have the general equation of the differential equation.
You're going to start with the differential equation that comes from rotational Newton's second law.
Okay.
Okay. That's where to start. So let's so we're going to derive the critical p-value for something that's pinned at the base. And let's just do pinned at the top too. Starting with the moment equation. Okay, so we're going to start with something like this. And this is V. And we have our big external force P pushing down, and our big external force P pushing up. And then we have a bending moment here at M. Okay? And we're going to use the fact that E, I, V double prime is equal to the bending moment for any x. Okay, so for the first step, just write out Newton's second law. Our about point is going to be here, and come up with the differential equation for this free body diagram. Okay, we're assuming, by the way, that this is that this distance is x. So the moment equation about that bottom point says we have a bending moment, and then we also have that's a counterclockwise moment of P times the deflection V is equal to 0. And now we make the substitution, and we get that E, I, V double prime plus PV is equal to 0. You can rearrange that. I usually do V double prime plus P over EI times V is equal to 0. Yeah.
So when you're doing the first step, are you like orienting the beam horizontally in your mind?
I'm not really. I'm just thinking of a positive deflection as being to the left.
Okay. I'm just not really seeing like how that becomes our rotational Newton's second law.
Okay. Well, let's see. Let's think about it. It's a rigid body. And there are only two loads. The first one is, let's say, is M, and that doesn't take any of this stuff into account, so that's... but the next one is P. What's the row vector, from the about point to where that force P is applied? That would be, you could think of that as X and then V.
So you are looking at it sideways then?
Oh, I guess, yeah, I mean my X, okay, yes, X is the vertical dimension here. What?
It's in the X component.
Yeah.
Vector.
Yeah, I'm using a coordinate system like this.
B is going to be in the Y direction. Okay.
So yeah, you can think of it as a turn coordinate system, or you can think of it as sideways with a regular coordinate system. Either way, like when we do internal loads in beams, we've never dealt with thinking about like a deflection like this, So, but yeah, if you want to think about it that way, you can.
So then the force is negative.
Yeah, the force is negative P0, and so the moment is PV.
Okay, thanks for doing that.
Yeah,
That makes a lot more sense.
okay. All right, now take a minute and come up with a general solution for that differential equation. this is where we're going to assume the form of sinusoidal functions. Okay. Okay, so now we're going to assume a form for the solution of V is equal to some constant times the cosine. And the argument of the cosine and sine both has to be square root of P over I times X. That's so when you take two derivatives, it has the effect of having a coefficient of P over EI. You know, that's, you're going to be multiplying by this square root twice. Plus C2 times sine of that. Okay. Now we are going to require that the deflection at x equals 0 is 0. This is the requirement that it's pinned at the base. Okay. I'm talking about, yes, the connection of the column to the ground is a pin joint, whatever, and actually, so it can do any crazy thing, but the deflection has to be 0 at that point. It looks like Dr. Seuss engineering. The question is, what happens when you plug x equals 0 into this function? So, you know, deflection at x equals 0 is C1 times the cosine of 0 plus C2 times the sine of 0. The sine of 0 is 0, so this goes away. The cosine of 0 is 1. And so what we get from here is that C1 is equal to 0. You see that we can't say anything about C2 because the 0 cancels it out no matter what it is. But we can say that C1 is equal to 0. And now we can update that function. So V of x is equal to C2 times the sine of square root of P over EI times x. Okay? And now the last thing we have to do is plug in what we know about another point on the beam, the end or the midpoint or whatever, and use that to find a non-trivial solution for this. So we're going to use the boundary condition at x equals L. To find a non-trivial solution. Okay, so take a minute. We're going to go, so the deflection at L is equal to 0. And so we're going to say C2 times the sine of square root of P over EI times L is equal to 0. And now you have to think about what arguments of sine make a sine function 0. So we have that the argument of the sine, square root of P over EI, times L has to be equal to so when is sine, it has to be equal to n pi for n equal to 0, 1, 2, so on. And now you can just square stuff and find the n that's the smallest non-trivial solution. So p over ei times L squared is equal to n squared pi squared. Solve for p. And you get ei n squared pi squared over L squared for n equals 0, 1, 2. Okay, well, the first one of these, n equals 0, says that the p-value that allows a deflection of 0 at the top is 0, you know? So, okay, if you apply no vertical load to this thing, there's not going to be any deflection at the top because it's not deforming at all, you know? But that's a trivial solution. So we want the first non-zero value of this p critical. So we're going to take n equals 1 in this case. And so our answer for p critical is ei pi squared over L squared. Yeah.
What happens to C2?
Well, it's just so there are only two ways for C2 times sine to be equal to 0. So anytime you have two things multiplied together, there are only two ways for it to be 0. One of the things being 0 or the other one being 0. Okay, well, C2, that would make this equal to 0, but that doesn't work for us, you know? That's a trivial solution because that would make our total deflection function 0. Okay, we're not looking for that one, you know? And so the only other way you can make this this deflection expression equal to 0 is to make the sine term equal to 0, and you do that with the arguments of the sine.
Does C2 have any physical significance in our model?
Yes. If you think about this as just a function, you know, that affects the amplitude of the sine function. And so, like, if you measured a greatest deflection of the whole thing, in this case, this would be just a single, you know, 1/2 of a sine curve. And so the greatest deflection would be at x equals L over 2. And if you measured that amplitude, that would give you the C2. But since all we're worried about is at what p-value you have to start worrying about this thing buckling, collapsing, we don't care about that. But it has the physical meaning of just the amplitude of the curve of the deflection.
So we don't have enough information to solve for C2 at this time.
At this time, we don't. I didn't give you that. Yeah.
Experimenting, and we wanted
Yeah.
to find a function for that v of x. We would put pressure on it, and then we would measure.
Yeah. Yeah, that's
and then
right.
we'd find C2.
Yep. But C2 depends on the load too, so it's, you know, I guess it's hard to imagine how it would be super useful, but I mean, maybe there would be times where you're not worried about, you're just worried about maximum deviations over time or something. You're not worried about it buckling, then maybe I could see that being useful. But for us, yeah, that never comes into it because we're just looking for how to make that equal to 0. Okay, so you asked, one of you guys asked for what if we just make up a place where this thing's restrained? What would this function look like? I think the answer is I've never done it. Let's do it right now. It'll be fast. But I think the answer is if you just pick a random point in there for the deflection to be 0, just say like, okay, I put a roller at 0.36 L. Okay, let's do that, 0.36 L. it's going to look like a very, very high P critical, but it's probably not very meaningful because we're assuming perfectly rigid rollers, perfectly rigid pins at the bottom, and none of that stuff is true. So it probably would find a much easier way to buckle. But let's see what it looks like.
Are you doing 0.32?
3/6. Yeah, that's important. So pinned at base and V equals 0 at X equals 0.36 L. Well, once we've gone through the derivation using what's happening at the base, we have this function that says this is equal to C2 times the sine of the square root of P over EI X. And then for the boundary condition, we're going to say C2 sine of square root of P over EI times 0.36 L is equal to 0. And so square root of P over EI times 0.36 L is equal to n pi for n equals 0, 1, 2, 3. And now we'll square both sides. P over EI times 0.1296 L squared is equal to n squared pi squared. We want the smallest non-trivial p, which means we want n equals 1. So we have that p critical is equal to E I pi squared over 0.1296 L squared. That isn't crazy high. But there you go. I mean, that's the, I guess that's probably small. That is definitely smaller than the P critical fixed at the base and pinned at the middle. But we only saw one value that had a bigger P critical than that.
What's the highest P critical we can get from one in?
I guess it just has to do with how far you are from being at the 0 of that sinusoidal function, you know?
So I guess the further you go, I would be interested to make a function of where it's pinned to the P critical to see as we move it, where you can see it. So I'm guessing the closer you get to the bottom, it'll be more like it doesn't exist.
But then you still have that large unsuperported section. You know what I mean?
Yeah, but the thing's still, right. And I don't know what happens. I think at some point it starts to be more of a just mathematical model than like a real description of what's happening. I mean, this is already making this assumption that this is an Euler-Bernoulli beam. This is called this elastic beam requirement. EIV prime is equal to M. That assumption is already kind of iffy, you know? I mean, so I don't know at what point I would stop trusting these values, but
I wonder if it would be like at the bottom, it would almost, if you put, the closer you get to the bottom, it would almost be as if it's not fixed at the top, it's free at the top, and fixed at the bottom almost. You know, because it'll have the
Oh,
constraints.
that's really interesting.
So maybe it would get closer to just being fixed at base, free at end. And maybe it would approach that value.
well, the thing is like,
In my head.
yeah. So if you have a beam that's like this, and say the rollers are here, you know,
Yeah, that's what I was saying. Where it's almost like it's.
and say you also have, I don't know, do you also have here or no? Nothing there?
I think he's right.
It's even if I squared it over.
Well, the differential equation that we have, the only solutions to that differential equation are sine functions. So how do you make a sine function be 0 at 1,000th of the length from the only way you can do that is having a very high frequency sine function. So the solution says that this solution would be, where'd it go?
You'd have to have really strong rollers.
Yeah, exactly. The solution says this is the only solution to that.
It would just be crazy.
You know, whether that's true or not, I'd really like to see a beam actually do that, you know, that does not seem super plausible to me, but that's what, I mean, once we made that differential equation, we were choosing how to model this thing. And according to the way we modeled it, this is the only solution that satisfies that.
Yeah, so at a certain point, it's just a model.
Yeah.
So say you're trying to like secure a column, how would you find the overall P critical with multiple